All right, welcome everyone to another video about TinyGo. And in this video, we'll be seeing how to design drivers while avoiding heap allocations. It will be centered mainly around heap allocations. I might touch on some other topic along the way if I feel it's relevant or if I just get their sense to, but mainly heap allocations, how to avoid them. Well, not so. Let me show you a little bit of a agenda for the video today. So first we'll be talking about why this is important. We'll look at some practical examples, PRs in the TinyGo drivers repo, a document which actually might answer some of your questions regarding good driver design. Still a PR, but might get merged to the TinyGo org website soon-ish. Surely by the time you watch this, it'll be merged and on there. Existing drivers, so more practical examples about drivers which get not everything, but most things right, according to these design document guidelines. And then we'll look at some drivers which can serve as like some examples of maybe what not to do so often. Of course, it's not like heap allocations just end your program or crash it. It is more than not something that accumulates over time and eventually may cause issues. Now with the addition of a new GC, maybe that's not such a big problem, but nevertheless, I think it's a good thing to keep in mind since heap allocations always have some impact. And then we'll go on to closing thoughts. So let's just get straight to it. Why is avoiding heap allocations so important to me? I say me because, well, I might think a heap allocation is not, I guess I might say it's, I might reject a PR because there's a heap allocation in there. And others might say, hey, no biggie, just one heap allocation, right? What bad could it do? It really is like, depends on your use case, right? Like some NASA will have vastly different rules for avoiding heap allocations compared to, say, me, because I still heap alloc every once in a while. So my experience has been working on, mainly my experience working on the CYW43439 repo. This is the driver for the Wi-Fi chip on the Raspberry Pi Pico. So let me just bring that up right now. So this is a driver that I've developed with the help of all these wonderful people. And what I mean when I say Raspberry Pi Pico W is this chip. So this is a driver so that the host chip controller, which we are programming in TinyGo, can connect to the Wi-Fi chip, which is this aluminum casing on towards the back. Funny to say, development boards have a front and back, but yeah, back, front. So, and that thing in the middle is the RP2040, which is a very well supported MCU in TinyGo, which there are some other videos on this, and this is Amazon.com in my country, in case you were wondering. So yeah, I have run into issues of people asking for better support. Maybe let's look at issues. So out of memory after running TCP tests for a while. Yeah, this was a bug reported by my partner in crime, Scott Feldman. He did a lot of the heavy work on this driver. I ought to thank him for that someday. No, I did thank him, but I'm always thankful for his contribution. Really feel like I couldn't have done it without him. So Scott here is detailing a bug seemingly in this repository, which after some time of running his program, there's a panic, runtime error, blah blah blah, out of memory. Now that just screams, you heap allocated too much, bro, and that this is the end of the line. Peace out, and then you get like the trace of where the panic happened. And what you know, it's inside of not the CYW, but inside of Seeks, which is used by the CYW package. Investigation into the issue revealed heavy heap allocation. So these two links right here, bam, just appending to a string that remained throughout the whole life of the program and just accumulated length. So this is fatal. So the reason this is such a big critical flaw in the program is because this string is incremented each time this is hit, right? And this, it doesn't just it makes a copy of this string every time this is hit. So because strings are, they're immutable, so you can't really append it to a string. Every time you append to a string, you're actually creating a copy of the string. So this is terrible. This created a lot of heap allocations, and this was same thing. These were added for debugging, as the name of this field implies, and I forgot to remove them after a release. So removing them actually fixed the issue, and we now have driver which does not allocate as much as it did back in this day, December 9th, 2023. So yeah, heap allocations can kill your program. Even though you have a garbage collector, which is supposed to clean up after you, it does on microcontroller units where the garbage collector isn't as sophisticated as the Go garbage collector, you're going to have these problems because it just can't keep up with the memory fragmentation. And I'm going over these topics a bit I'm not going into too much detail on what the garbage collector is, what a heap allocation is. I'm kind of like supposing you all have some sort of background on that. In any case, if there's this page on driver design will be up soon. Oh, whoa, this is not it. There's driver design patterns for the Linux kernel there. Very interesting. That might actually be a good link to add here. This will be up soon. It's under documentation, guides, driver design, and development. Should be up by the time I finish this video. So let's and there's what I was going at is there's a little bit of an introduction on heap allocations. Still doesn't go into too much details as might be necessary for someone who's totally new to the idea of a heap. But yeah, there it is. And the reason I'm making this video is because a lot of questions come up regarding some suggestions I make. So there recently was a PR that I'm not going to show the specific PR, but there was a PR in the TinyGo drivers repo adding a new driver, and there was just so much to cover on making the driver more resilient to these crashes, sort of like having in mind all the different ways the user can use the API to eventually maybe start generating garbage that might become fragmented and eventually crash the program, like it happened in the issue in the CYW driver. Well, so many things come up that, well, I eventually wrote up this document, which I just showed you, so I could link this to users who could maybe get a better idea on how to design a driver. But even with this document, I still get questions on, hey, how do I write this? So I thought I'd make a video. Might be easier to follow, has more of a, back and forth sort of. I got my mouse to point at things on the screen that might like actually give a little bit more of like an intuitive sense of what I'm talking about. So here goes. Yeah, without further ado, let's get into existing drivers. Let's look at two drivers which are pretty well designed. So there are links here. So let's look at this PCA 9685 driver, written by, I think I might have written this and Ron formatted it. In any case, look, we start seeing some of these heap avoidance patterns already. The device struct is as simple as possible, made in order to avoid heap allocations. I mean, you got your I2C bus, your address, and you got this that might be unfamiliar. If you've been developing drivers without writing in memory in these arrays which help us avoid heap allocations. If we read into here, we'll see that this buffer is used almost exclusively in truth, not inside the write reg function as I would have expected, because blah blah blah, this actually has an IO file. So I was not expecting this actually. This driver actually uses the legacy I2C API, which may perform allocations. Occasionally, the compiler can optimize it and remove the heap allocations, but this is actually not a pattern we'd use if writing a new driver from scratch, because legacy read register can perform a heap allocation. So what I mean by that is if we open read register, right, it receives the I2C bus. That's an interface, and since you're passing in the interface, this is never going to allocate. This argument is a integer, blah blah. What is interesting is data. Now, data is a referential type, so it has a pointer within it because it's a slice, and that is where it gets problematic. Because if the pointer to data, the pointer to the underlying byte slice is held by the implementation received, so by this bus.tx, if this method holds a pointer to data, that slice, the data which this slice points to, is going to escape. So we're going to have a heap allocation here. Maybe I can do some drawing, right? So say we have, yeah, so we have, like, the way I like to think about slices is the drawing tool is not the best part of Linux Mint, for sure. So we have, yes, there we go. We have perfectly straight buffer, contiguous memory. And you can think of this as being little bytes, right? And on it goes. Now, if, and this is position 0 of our, let's see if we can, bam, yeah. That's position 0 of our slice. So if we do, this is the first byte, so S buff 0, bam, that's buff 0. We can even help you guys out by writing some buff 0, yeah. This is the buff slice, so a slice, unbeknownst to many, is actually this data structure. So it contains a pointer to the underlying data type, underlying array, sorry. And it's got length and the capacity, and we don't really care about the capacity. You can do really cool things with the capacity in designing drivers, but we don't care about that right now. That's a more advanced topic. We care about this pointer to the start of the buffer and the length. That fully defines, like, the data we want to write over I2C, right? We know where the data starts, and we know how long it goes. So we know we gotta write n bytes. And actually, that wouldn't be the nth byte, right? This would be position n. The nth byte, right? Because we're indexing in 0. So, bam, we got the whole data, right? We got where it starts, we got the length, and that's how when we pass the buff over to TX has access to that data. It has a pointer and a length. Now, if TX, for some reason, keeps a pointer to that data, then that data escapes. It is the wording we use when talking about. I'm sorry, this coffee, so good, but it's kind of powdery. Washing down that powder with more coffee. So we might have a problem here because maybe TX keeps an address to buff. If the compiler can prove it doesn't, then there's no need for the data representing buff to be on the heap. However, in this case, and in practically every single case in the driver's repo, we are using interfaces. So these are the types we use. Oh, I'm going to zoom that in. These are the types we use for interaction with our host drivers, SPI, I2C. We use interfaces, which is awesome. I mean, like, this makes life so much easier because when we write a driver, it's generic. It works for every single microcontroller which has an I2C interface which implements this method. An I2C implementation which implements this method. And you can, if you're curious about where our implementations live in TinyGo, you gotta go to TinyGo, TinyGo/TinyGo, and we go to machine under source, machine, and bam, look at all these I think it's like the number of microcontrollers we've implemented is up to 100 by now, or is that development boards? I'm not sure. It's a whole lot. And look, if I look for the RP2 SPI, this is one I think I've written myself. This is the concrete implementation of SPI. So we look here, here's TX. And we were just looking at I squared C, but SPI also has its method set, and it's, look, TX, not to be confused with the I squared C TX, which requires an address, but SPI has TX and transfer. And if we look at here, TX and transfer. And what you know, like, it's that easy to write generic code, because now in our drivers, in this PCA 9685, we just write in drivers.I squared C, and I don't know what implementation is going to be behind drivers I squared C. It's going to be, it might be an RP2 SPI type here, machine, or heck, it might be an STM32. Hopefully I can find STM32 SPI. Oh no, yes, here it is. Or it might be this guy. Configure, transfer, here it is. Transfer W byte. It's a bit more complex. Hey, well, this guy, I'm guessing maybe the TX method is somewhere else, but rest assured, yeah, it's probably an STMF7X2. 7X2 maybe here. Or maybe it's in SPI TX. There we go. So occasionally, so we do have this code, SPI TX. This code that where a host only need to implement the transfer method, and then this is included for hosts which only have the transfer method, and bam, the TX method is automatically implemented. And this is some build tag facilitation, so that, you know, we only have one TX method for hosts which, you know, only have the transfer method in their HAL, which is not the case for the RP2, which we just saw. But enough about that. I'm kind of going off on the limb here. What I was going at is, these are interfaces, and they do provide this super awesome facility of not needing to know what the implementation is, but on the downside, not knowing what the implementation is also means we don't know what the caller does with these referential types, these slices. So the caller might hold on to that reference, in which case the compiler needs to mark that memory as escaping to the heap, and that forces that memory to be allocated on the heap. Now, if that memory, you know, is just one buffer you're reusing the whole time, that's no big deal. I mean, it's going to be allocated on the heap on initialization, and then you just, for, you know, no more allocations throughout the life of your program. So if initialized correctly, then you're good, you're set. What might happen is you make one call, you create the buffer on every call, and then pass it into the TX method. And that's where the problem rises. Here, you're creating a slice every single time you call read register. And every single time you call write register, you're creating you're creating you're creating a buffer every time you call write register. So both of these will allocate this anonymous byte slice, and this guy's going to allocate this slice, which might be much longer. This is only 1 byte allocation, but that might be tricky, because a heap allocator is probably not going to allocate a single byte every time this is called. I mean, there's a minimum size for a heap allocation, so this might actually allocate 8 or 64 bytes depending on the garbage collector you're using. So yeah, these are gonna allocate because that's an interface and that's a slice, and you're creating it here, so pretty easy to see that this is gonna allocate. And so with that, I conclude talking about how this legacy in I2C interface is how we used to do things. We don't want to do it this way. We'd much rather do it another way. And I'm really hoping the next example is an example which does not use the legacy interface. So, oh, but look at this. Well, but it does. So CMD measure, where does CMD measure come from? Okay, interesting. So the creator of this driver created these global variables which hold the commands at compile time. So these are going to be defined at compile time, and looks like that's all you need to actually interact with this driver. Just send these constant commands. So write register, boom, enact command, send, read register. Hopefully I'm not missing any files, right? IO files? No, there's just one file in this directory. So this might allocate. Look, this person is creating a 2-byte buffer, passing it to TX, danger, and boom, heap allocation right there. This escapes because it's passed into TX. It receives, both of these. It's actually one single buffer. It's 2 in size, and then here it escapes. So, oh boy, looks like the drivers I listed here are no bueno. Is there even one single driver which is not an allocating driver? This one has a buffer, but yeah, it uses a legacy interface, so it does try to like not allocate, but hey, legacy interface, we know that allocates. You know what? I do know of one. I do know of one PR which I think might not allocate. And it's this rewrite. Here we added the data buffer. So this was a modification of the MPU to avoid heap allocation. So this was the old interface, right? Now it's legacy read register. Well, before it was a method on the I2C interface. This had 2 more methods: read register, write register, which just called TX underneath. So it was just allocating for a facilitator to allocate. And this PR tried to remove those allocations, as well as standardize the interface to use like a different API, like more in line with the driver sensor interface, which maybe more on that later. So yeah, looking at this driver, write 8, probably at the end. write mask. So here we do have a buffer, calls to read and write. Do these allocate? Okay, they do. So as you can see, audience, it's very hard to write a device driver that does not allocate. All of these allocate. Even when the author of the PR was me, not that long ago, it is really hard to write a driver that does not allocate. No, it's not hard. It's actually you just have to be mindful. You just have to, keep your eyes open, look for those heap escapes. Let's carry on quickly. I'll show you tools on how to avoid. Actually, we're close to the end. No, we just gotta look at a couple more examples. Let's look at the ST7735, which has a very nice systems engineering analysis perspective we can touch up on. Here we have ST7735 driver. So device. So this device calls configure here and does a bunch of data writes. And now if you're looking at this, you might think, whoa, dude, do I really need to call data every single time, or can I just call it with a buffer? Maybe the creator of this API is created data to avoid a heap allocation, since this is an integer. You can't escape an integer. It's but the truth is, let's look at data. Okay, that's not helpful. Func BGR might be TX data. Here we go. Sadly, this does escape as well. So, and boom, you're creating a slice right here. You're calling TX. Data is this slice you just created, and data is passed into the interface. So compiler can't really tell if that data is escaping, and it allocates it. And we can is an excellent time to make use of our tools we have for heap allocation analysis with TinyGo Advanced Edition. So I'm here. I've cloned the drivers repo, and I'm looking at the examples. And there's one example on how to use the ST7735. I've actually gone ahead and modified it because it was written for some microcontroller, which I'm not entirely sure which one it was. I can tell which one it is because I can look at the smoke tests. So if I go ST7735, not here, boom, microbit. So the example is written for the microbit, and this is in smoketest.sh. You can try this in your own time. So I'm actually going to go ahead and go. I've modified these. Git reset. I'm going to just reset them. See what happens. All right, rm, all those ELF files I've generated, just for kicks. So if I go ahead and build this, TinyGo build target goes microbit. I'm actually going to print Alex. This is showing you the tool I use to detect those pesky heap allocations. 735. If I build that, let's actually zoom in a bit. Boom. I get a list of heap allocations. And interestingly enough, it seems like the state of things is much better than I thought. So the only heap allocation is when calling new image. That happens in the configure call of display. And right here, pixel new image. This is something people do. They allocate at initialization. It's actually like, something the NASA even says is okay, because hey, if you're just configuring your peripheral at startup, you can allocate here. That's fine. You'll be allocating once in the entire lifetime of your program, and then you'll be using the screen. What happens if the user wants to configure the screen repeatedly? That's where the problems might arise. Now, these are the arguments to configure. So the width and height of your screen that's not changing throughout the lifetime of your program. Don't know about the row offset and column offset. I think that's like a display thing. Maybe I'm going to go ahead and say that's not changing throughout the lifetime of your program. Model, I'm not sure what this is. Oh, that's the model of your screen, perhaps. Isn't there like a... Oh, green tab. Yeah, so that's probably like the model of your screen. Driver's rotation, aha. What if a driver wants to rotate the screen in the middle of your program? They're going to call configure with a different rotation value, and then you'll hit this line of code right here that we're in configure, and you're going to allocate a whole new screen buffer. And this is very expensive. Now, I can guarantee no one's calling configure more than once every program, almost with certainty. Who knows in the future? Maybe once TinyGo is more popular used, maybe that's a thing people do more often. The way you can mitigate this heap allocation is by actually checking if batch data is initialized. So, bam, bam, bam. You can actually check if the length is less than the deep batch length, then we know we gotta allocate, right? Boom. And if it isn't, we know we already created the screen, and it can fit our current screen size. So we do batch data and do d dot we don't have access to the raw buffer in a way that so we could set it. So maybe I'm guessing we can just, do nothing about it. Not really sure, but maybe that's an issue with the Pixel API. Maybe if we want to reuse the buffer, maybe we need some more API on that side. So, but maybe this is enough. Maybe, if the length is greater or equal to, then just reuse it, no problem. What else? That's just one thing I wanted to show y'all, is this idea of reusing memory, which is already allocated, as a way to avoid heap allocations. And then, oh wow, I have all these, so much stuff open. Again. I wanted to try out what happens if, because I do recall this allocating more stuff with a different target. I know this is probably not going to build. We're going to have to like do something like machine. Just make these all LEDs. LEDs. And maybe then... Aha! Now that's curious. It doesn't allocate on the microbit, but it does allocate on the pico. And well, let's go to the specific lines which are now allocating, which were not allocating beforehand. We have this tool, which is print_allocs, which is telling us, hey, this, boom, line 421, data escapes, right? Not data, but this slice we're creating, anonymous slice. It has no name. Is escaping at line 421. Same line and that's presumably because tx function has been marked as a function that escapes its data, although the truth is it's actually escaping here, 427. And the way I know that is because, well, bus is an interface, so it's very likely the reason it's not allocating. And if I remove it, hey, the heap allocation disappears. So this is a very important tool that everyone should have in their tool belt when analyzing heap allocations. The print_allocs flag, which is key. And we just see that, yeah, pretty much every single time tx is called, no surprise, allocation. Surprise in the previous case where it wasn't allocating when building for the microbit. I guess, worth reporting to someone who knows more about compilers than me. Alas, that is everything I wanted to talk about relevant to the ST7735. Next up, let's... the BME 68X. Well, I kind of don't want to go into too much detail with this PR because I don't know if the person wants to, get feedback on video on YouTube. I will just, go over it very, very superficially. I think it's right here, right? Here, add support for the BME. Carlos here has submitted this PR, and it is a great addition to the TinyGo ecosystem of drivers. I did jump on a call with him, and we talked about possible betterments. He did have some interesting counterpoints to some of my comments regarding the functional options way of doing things. It is true, Carlos argues that functional options are actually good for like making constant configuration explicit. So with this way, there's no way that the user can think that the think about like actually I'm actually having second thoughts about Carlos's argument. So Carlos would argue that with a configure method on your sensor, if you pass in a config struct, like most drivers in the TinyGo repos do, users might think that, editing the configuration after configuring the sensor might be reflected in the sensor, and that's confusing. And that, I actually thought that was a really good point, like readability wise, new users might think, I can just edit my config after configuring my sensor and it will be reflected. But on second thought now, this is actually a slice. And you could actually make this a value. You could actually make this a slice value up here and then edits it. It's kind of stretch. Anyways, Yeah, let's look over the file. So configuration options, kind of a hot topic. I was almost willing to like consider like trying out functional options, but they do give. When I say functional options, I mean oh, this is not it. Arguments to new, but I'm looking for the options here. These. So an option is defined as a function, and this is a great pattern in Go for APIs which change over time, because it lets you add functionality very flexibly without sticking to a configuration struct which has its types defined, and you can't really add much more in there. Whereas with functional options, it's like there's a lot of data you can pack in there with the option type. Now, my argument was, hey, we're developing drivers. Like once we finish the driver, that API isn't changing ever, because that peripheral is manufactured. Your requirements are done. Like no one's going to add a feature. No one's going to ask for like, oh, but what if it could do? If you've designed the API implementing all the hardware features, that's it. It's game over. And that's a really nice thing about developing drivers. Like you can be actually done with the software. You can say, hey, this is done. I'm never touching this again, because you've implemented all of the features in the hardware. No one could possibly ask for more, because unless like a security vulnerability is discovered, in which case you for sure want to make your changes, although that might not be such a common event since we're using Go, and Go is memory safe. I will regret my words one day. but yeah, you're gonna be like, closing projects much more often if you design drivers, if you develop drivers, because hardware just doesn't change once it's manufactured. That might change in the future, with all this IoT craze going on, but it is not the day yet, so rejoice. These are very nice. Defining types for your configuration options. This is a very nice way of doing things. If sometimes the datasheet you're reading actually sets values for the coefficients, sometimes those values are literally just 0, 1, 2. Iota in Go is like enum generator. This is going to be equal to 0. This is going to be 1, 2, 3, so on. So sometimes maybe this is the case. Maybe where does Carlos use this? But yeah, enums are very nice for configuration options, because it lets the user know exactly what options are available, instead of giving them like an integer and being like, hey, this is my oversampling. And they're like, okay, what does 0 mean? I don't know. It's an integer. Try it out and see. But instead, doing it this way with the enums lets the user know exactly, oh, I'm setting my coef, filter coefficient, to 2, 4, 8. And they can read up on the datasheet, or you can actually document here. You can actually add Carlos ahead of me, Carlos has added a comment to say, hey, coef 0 is no filter at all. Sampling off turns off sensor reading, and look at it. What more could you ask for? Standby for 500 milliseconds. I'm gonna go ahead and maybe do a little bit of complaining. I would like to see MS back here. It would let me like not have to read up on what exactly this is, and this could be 0 59S. And I think that would be like a nice change, you know? Because here, hey, what is this? Is this 62.5 seconds or is it 62.5 milliseconds? So just a little minor nit right there. But overall, very nice addition. And yeah, I already thanked Carlos for his contribution. It's looking really good. Yeah, just your usual heap allocation, you know. We just looked at my drivers and they do pretty much the same thing. So can't tell them nothing. This might look like a heap allocation, but since this is a constant, and the way I know it's a constant is because it's written in caps, and that, you know, usually points to some term of the datasheet. Since this is a constant sized buffer, the compiler usually is pretty good at saying, oh yeah, this is, I can put this on the stack since it's always the same size. But here, you know, bus is called with TX and this might allocate. So what else is left here? I think I've gone over everything I've really wanted to go over here regarding heap allocations. So enough fun. Going back to, let's go to the CYW 43439 driver and do a deep dive. Maybe not so deep. Okay, whoops. Okay. Code CYW. And here we go. This is the CYW driver, which I mentioned earlier in the video. Let's bring it up. Bring up the page just for completeness. Showed this earlier, but just so you can find it right now, it's under soypat CYW43439. This may be moved in the future, so if you go over to this URL, you might find it's moved over to maybe the TinyGo organization. As of now, we're still not sure whether that's a good move, seeing it might break users, and there's quite a few users who use this repo. So what is left? Oh yes, I wanted to show you all a complicated driver. So let's close these. This is what I'd consider a complex driver. It's a Wi-Fi chip. It's like a coprocessor. You know, you're basically controlling another microcontroller. And there's a lot of registers and even more buffers than you think you might ever need for interacting with a driver. And the reason for these buffers is because, like we've seen, we use arrays in our device struct to avoid heap allocations. And we need 3 because there's like 2 transport layers for the data we send over the buffer. So I might bring up a drawing, like just give you an idea of what we're doing here. What I mean when transport layers. So let's go back to that image of the buffer. Yes. And here we go. We have position 0 of our buffer. And if we do buff 0, that's where this points. When this driver has when I say this driver has 2 transport layers, I mean to send data, you need to put it into into two buffers per se. Not necessarily, but here. We have the buffer that we send over to the Wi-Fi processor. In it, we have an IOCTL header. Oh, that's not red. So if I look for IOCTL, let's just look for header. Remove SDIO header, maybe we can... here we go. And this is where we have our headers defined. Do we have the sizes for these headers? CDC header, BDC, blah, blah, blah. There is an IOCTL header. Maybe I'm imagining things. Maybe it's the BDC and SDPCM. So, yeah. So as you can see, lots of headers. And a header is basically just like data you have to put at the start of your buffer that describes the rest of the contents of the message. So maybe this is the SDPCM header. And then, because you're implementing a protocol, that's how protocols sometimes work. You send your data with a header, describes how many bytes there are, what priority it has, and then after the SDPCM header, you also have your, maybe, not really sure, maybe the order is inverted, but your BDC header. And only then are you allowed to put in your data, which might be, in the case of the CYW driver, let's use green. In the case of the CYW, it might be your Ethernet and TCP, your TCP packet. Let's say it's a TCP message, which it itself contains more headers. So maybe in there you have your Ethernet, right? But we don't, the driver doesn't care about the headers in this packet. This is the data you're sending over your Ethernet interface. The CYW43439 implements an Ethernet interface. So yeah, you're going to put your Ethernet header right there. But all this data is just a blob you pass into it, and it just handles. It doesn't really care about this data. It does care about this. The driver needs to implement packaging of both of these headers. And the user is sending in this header, the TCP header. So, and these headers are not even there all the time. Sometimes, they're different size. Sometimes they have padding. And so what you end up with is needing to receive the header, this header, and then first maybe you package it with the PDC header, and you package it into one buffer. And so you have one buffer along the way with the BDC header. So this might be one of the buffers we use. We use the send IOCTL buffer, perhaps for this. So send IOCTL buff. And then, this needs to be packaged with an SDPCM header. So then you can't add data up here in front. You've already packaged your data inside a buffer, starting from the start. I mean, you could be smart and leaves room in front to put in the SDPCM header, but that's kind of hard. You need to know which header you're using, or use max size. it's hard. All right, using this was a complex driver. I had to have 3 buffers to like package the data correctly. This could be optimized. Maybe you're smart. You know how to optimize it. If so, please help me. May this spark some ideas, and you want to show off. Well, please, you are more than welcome to show me how it is done. But yeah, and this would be the other buffer, IOVAR buffer, IOVAR, maybe. And there's another buffer, which means it's not, there's probably another header I'm forgetting, a situation where there's 3 headers. There's a lot of layers of abstraction in this. I'm calling these layers, it wouldn't be layer abstraction, it'd be like protocol layers. There's lots of protocol layers in this driver, which make it require lots of buffer data. Each one of these is 2 kilobytes in size. That's like 1%, a bit less than 1% of the memory available on the Pico. So, bam, you're already hitting like 3% memory usage just by using this driver. Which, to be fair, is not that much memory. I mean, for having Wi-Fi functionality, still, this could be better. At least it doesn't allocate. That's the important part, because I don't strictly need this. I could just do without it, but then I'd have to allocate every time I want to send data over the buffer. So that's why we have it. We allocate a lot of data at initialization, and then we just use that data. And that is the magic of programming drivers while avoiding heap allocations. If you got this far, thank you for your attention, for listening. There's not much left to say. This is hard stuff. I mean, you probably won't be doing this. Only insane people, i.e. myself, and really generous and nice and outgoing people, these things only me and really nice people do. Like, for example, Scott Feldman and Ron, who've been contributing so much to this project. I really gotta thank them. They are not insane. I'm the insane one, if anything. And what else is left to say? Again, once a driver is written well, no more changes are required. No one's gonna add features to the hardware you got laying around in your house. That hardware's staying that way forever, for good. New hardware might come along, and we write new drivers for new hardware. But existing hardware, not so much. And that's it. I hope this video was informative. If it was, if you liked it, leave a like, maybe subscribe. And if you didn't, well, just hit that dislike button like there's no tomorrow, and leave me a comment on how I can do better. They actually do help. This microphone I bought thanks to a suggestion of one of my kind viewers who point out my audio was terrible. They didn't really say that, but it was pretty obnoxious to listen to. Hopefully I didn't forget to turn on the microphone. Doesn't look like I forgot. So that's it. Thank you for watching. See ya.